Let's say we drilled a well in a transition zone with both oil and water contained within the pores. Can you guess which fluid will tend to be produced and which one will tend to stay within the pores? Will they both be the same with respect to the ease of production? Does their production depend on their types, or the rock type, or both? In order to know, you have to be familiar with a term called wettability. Wettability is the tendency of a fluid to adhere to a solid surface in the presence of another immiscible fluid. This fluid is called the wetting phase of the rock. It represents the layer which adheres to the grains from inside the pores, while non-wetting phase exists at the center of the pores. Non-wetting phase fills large pores first and is easily produced. On the contrary, wetting phase fills narrow pores first. It represents the fluid that is difficult to be produced. In nature, all rocks are water wet. However, oil-wet rocks exist due to wettability alteration. This is caused by different chemical reactions which may happen in the reservoir. For example, deposition of heavy organic matter as asphaltenes and paraffins over a long reservoir lifetime. To quantify wettability, the contact angle must be measured. This angle represents the angle between the tangent of a droplet of a liquid and the solid surface in the direction of the denser fluid. So, if we have an oil-water system inside rock pores, the contact angle is represented by angle theta instead of angle alpha. That is because water is the denser fluid. There are three different ranges of values for the contact angle, with each range indicating a different result. First range, theta is smaller than 90. This means that the fluid represented by the droplet is the wetting phase. It has the ability to spread and adhere to the solid surface. The lower the contact angle value, the higher the wettability. Second range, theta is higher than 90. This is the opposite case. The fluid represented by the droplet is the non-wetting phase. The solid surface repels that fluid away from it. The higher the contact angle value, the higher the repulsive force. Third range, theta is equal to 90. This is the case where the ability of both fluids to adhere to the solid surface is equal. Hence, the solid surface is called intermediate wet. Measuring the contact angle is not the only way to quantify wettability. It can also be quantified by means of the Cecil-drop ratio. It is the ratio of the height of the droplet on the solid surface to its breadth. A Cecil-drop ratio of 1 indicates a complete non-wetting action of the droplet phase. On the contrary, a Cecil-drop ratio of 0 indicates a complete wetting action. Quantification of wettability by any method requires lab tests. Unfortunately, wettability of the core can be altered before reaching the lab by several reasons. First reason, it can be contaminated by drilling mud. Second reason, pressure and temperature changes due to the core trip from the reservoir to the surface can cause fluid composition changes, and hence causing precipitation of asphaltenes and waxes, which lead to wettability alteration by coating rock grains. Third reason, exposure to oxygen can lead to changes in the chemical composition of fluids, causing the generation of surfactants which may affect the core. As a solution for such a problem, core can be cleaned to restore its initial condition first. Afterwards, it's saturated with formation brine, then flooded with crude oil at reservoir pressure and temperature to simulate the exact environment of the reservoir. However, variations in the composition of crude oil and brine between the formation and the lab can lead to wrong wettability measurements. None of the methods for measuring wettability can be considered as 100% precise. This is the main reason for driving ongoing researches on wettability measurements. If you liked this video, please support us by hitting the like and subscribe buttons below. Don't forget to share it with your friends for their benefit. Thanks for watching.